Hello students, let us continue our ongoing chapter 9 hydrocarbon. This is our theory part 10 and today we will cover the NCERT section 9.3.4 in it. So this is our disclaimer. The learning objective of today's class would be to understand various preparatory methods used for the preparation of alkenes. Okay. Now if I talk about the specific name of the NCERT section, then we will be covering NCERT section 9.3.4, which is preparation of alkenes. So we are going to explore the methods of preparation of alkenes. Alkenes are hydrocarbon with at least one double bond within its structure. They are important in the chemical industry for producing polymers and other chemicals. So it is very important to learn their preparation methods. The first method that we will discuss is partial reduction of alkynes. Alkynes are hydrocarbon with a carbon-carbon triple bond. By partially reducing them, we can convert them into alkenes. This process involves adding hydrogen to the alkynes, but only enough to form a double bond instead of single bond. The second method is dehydrohalogenation of alkyl halides. Alkyl halides are compounds where a halogen atom is bonded to an alkyl group. In this reaction, we remove a hydrogen atom and a halogen atom from adjacent carbon atoms, resulting in the formation of a double bond, thus creating an alkene. Next, we have the dehalogenation of vicinal dihalides. Now, vicinal dihalides have two halogen atoms present on the adjacent carbon atoms. By removing these halogen atoms, we can form a double bond between the carbons, resulting in an alkane. Finally, we can prepare alkene from alcohol through acidic dehydration. In this process, an alcohol loses a water molecule, which involves removing a hydroxyl group and a hydrogen atom from adjacent carbon atoms. This reaction is often catalyzed by an acid and it results in the formation of a double bond, creating an alkane. Now, let's start preparation of alkenes by our first method, that is from alkyne. Alkynes can be partially reduced to form alkenes. This process is important in organic chemistry for modifying the structure of hydrocarbons. Now, we see that when alkynes undergo partial reduction, they form alkenes. This is a key transformation in organic chemistry, allowing us to convert triple bond into double bonds. The type of alkene formed during this reduction can be controlled by the catalyst that we are using. Specifically, the catalyst determines whether the resulting alkene will have a cis or trans configuration, which affects the molecule's properties. Let's delve into the role of Lindlar catalyst in this, which is used for non-terminal alkynes. This catalyst is crucial for selectively forming certain types of alkenes. The Lindlar catalyst is used for partial hydrogenation of alkenes. This means it helps to add hydrogen to the alkyne, but only enough to form an alkene, not an alkane. In the presence of Lindlar catalyst, which is a partially deactivated palladized charcoal, non-terminal alkynes are converted into cis alkenes. So this is very, very important. The selective reaction is useful in synthesizing specific alkene structures. So here we have an image illustrating the reaction process. The visual helps us to understand how the Lindlar catalyst facilitates the conversion of alkynes to cis alkenes. Here we have alkyne, that is acetylene. When we do the reduction with hydrogen in presence of PD/C, which is palladized carbon, cis alkene, that is cis ethene, can be formed. So if you are taking acetylene, then it will result in ethene, following this generic path, where we find that both our alkyl group are on the same side and both hydrogen are on one side. So this is our next example, where the reduction of but2-ine is done with the Lindlar catalyst. So it results in the formation of cis-but2ene, where we find both CH3 are on one side and both hydrogen atoms are on the other side. Therefore, this given structure is of cis type. Now, we will see the role of Lindlar catalyst in the reduction of terminal alkynes. So terminal alkynes are reduced using Lindlar's catalyst. The result of this reduction is the formation of alkene. This is a key step in organic synthesis, allowing chemists to create specific types of hydrocarbon with double bonds. So an interesting point about the alkenes formed from terminal alkynes using Lindlar catalyst is that they cannot be classified as cis or trans. This is because your terminal alkenes have only one substituent on one side of the double bond, making the cis trans classification irrelevant. So this is your reaction. Here we have a reaction illustrating the reaction of terminal alkyne with Lindlar catalyst. Now it results in the formation of ethene, which is incapable of showing cis-trans isomerism or geometrical isomerism. We can also take propyne in place of ethene. So here propyne contains a terminal alkyne which reacts with Lindlar catalyst, which is palladized carbon with hydrogen, to form propene. Now propene has no cis-trans possibility because the end carbon has same group present on the hydrogen part, right? You can see here that the end carbon has two hydrogens, and since they are identical, therefore your propene cannot show cis-trans isomerism. Next, continuing looking at the preparation of alkenes from alkynes, which is also called the partial reduction. Now we introduce the Birch reduction. This is a specific type of chemical reaction used to partially reduce alkynes, which are hydrocarbon with a carbon-carbon triple bond. Now, we see here that the Birch reduction involves the reduction of terminal alkynes using sodium in liquid ammonia. This process results in the formation of alkenes which has a carbon-carbon double bond. So this is your example. At this point, we have an image that visually represents the Birch reduction. So we have taken propyne and the propyne is converted to propene. Again, here also we don't have to worry about the cis or trans configuration because the given alkyne is a terminal one. Now suppose you take the Birch reduction and try to impose it on non-terminal alkynes. Then what will happen? If you react your non-terminal alkynes with sodium in liquid ammonia, it forms trans alkenes. Now, on contrary or opposite to the Lindlar catalyst where cis was the predominant product, here we are getting the trans alkene in Birch reduction. Now, here is a general scheme for that. You can see here that the RC triple bond Cr plus H2 is reacting with sodium in liquid ammonia to give us trans alkene because the two R's are present on opposite sides, right? And same can be said about the hydrogen. Finally, we can just apply this same on a specific example such as bute-2-ine. So bute-2-ine undergoes Birch reduction and it gets converted into trans-bute-2-ene because here both CH3 are present on opposite sides and both hydrogens are on opposite sides. Moving on to the next process of forming alkenes, which is from alkyl halides through a reaction called as dehydrohalogenation. If we want to define it, it is very simple. So this involves removing a hydrogen atom and a halogen atom from adjacent carbon atoms, leading to the creation of carbon-carbon double bond and the release of a hydrogen and a halide. Therefore, we call it as dehydrohalogenation. Now, let us look at how alkyl halides, when heated with alcoholic potassium hydroxide, undergo a reaction where they lose a molecule of hydrogen halide to form alkenes. So hydrogen halide is represented by HX. This is a key transformation in organic chemistry. Now, we can just use a general reaction to represent the whole scheme because we are taking three types of halide here, remember, only chlorine, bromine and iodine. So X is representing a halide. Now when we react this given alkyl halide with alcoholic KOH in the presence of heat, it is getting converted into an alkene through the process of dehydrohalogenation. Now reaction involves the removal of hydrogen from beta carbon. Now what is beta carbon here? the carbon which is just next to the carbon containing halogen. So the halogen containing carbon is named as alpha and the next adjacent carbon is named as beta. Now the reaction involves the removal of hydrogen from the beta position, the carbon next to the one holding the halogen. Therefore, it is also named as beta elimination reaction. Remember, it's a very important term here. We can also call it as beta elimination reaction because the hydrogen is removed from that carbon which is adjacent to the carbon containing halogen. Got it? Now, what is the reactivity order? It is seen that halogen are being less reactive if we are increasing the electronegativity. So, iodine is the most reactive one. So basically, if your alkyl halide is containing iodine as the halogen, then it is the most reactive. Then comes your bromine, and lastly comes your chlorine. If you do the same comparison for tertiary, secondary, and primary, then tertiary is the most reactive one. So if your alkyl group is a tertiary one, it's the most reactive. Next is the secondary, and lastly is the primary. So this order is very important for predicting the reactions outcomes. Moving on to the next process, which is dehalogenation, and this process is done on vicinal dihalides. Now this is a fascinating reaction where we remove halogen atom to create alkenes. First of all, you should know what is vicinal dihalide. These are compounds where two halogen atoms are attached to neighboring carbon atoms. You can look upon an example here. See, we have a vicinal dihalide. You can identify this vicinal dihalide by looking at the position of two X's which are present on neighboring carbon. Now, if you react this thing with your zinc, it results in the formation of alkene and zinc dihalide. Now, dihalide with halogen atom present on adjacent carbon is reduced by the zinc metal. So, zinc is acting as the reducing agent here, and this is also a type of elimination reaction where the halogens are removed. Remember that eliminating means removing. Now let us have a look on some specific chemical reaction for the given chemical equation for the given reaction. In the first equation, the ethylene dibromide reacts with zinc to form ethene gas and zinc bromide. In the second equation, 1,2-dibromopropane react with your again zinc to form propane gas and zinc bromide. This process is a practical way to produce alkene, which are important in the chemical industry for making plastic and other materials. Now let us explore how alkenes can be formed from alcohols through a process called acidic dehydration. Now let us look at the concept of acidic dehydration. This involves the elimination of one water molecule from an organic molecule, which when an acid is present. It is a key process in organic chemistry for transforming alcohols into other compounds. So, we see that when alcohols are heated with concentrated sulfuric acid, they undergo a reaction where one water molecule is lost, resulting in the formation of alkene. So, this is an important reaction for creating unsaturated hydrocarbon. The reaction here shows a general scheme where we are representing the alkyl group with R. So, when we take a alcohol, then in the presence of concentrated sulfuric acid and at an elevated temperature such as 443 Kelvin, the alcohol is dehydrated. Dehydration means removing water. The simple logic of dehydration is removing water. So we are removing the colored H and OH to give us the alkene, which are later forming the water molecule. Now, here also the OH group is removed from the beta carbon. You can see here very clearly. Okay. Sorry, the hydrogen group is removed from the beta carbon or the adjacent carbon. Therefore, this reaction is also serves as an example of beta elimination reaction. Remember in the previous one where we are reacting our halogen, there also the hydrogen was removed from the adjacent carbon where the halogen was attached. Here also we are removing hydrogen from an adjacent carbon where OH is attached. So both reactions are an classical example of beta elimination reaction. Can we take some specific example? Yes. So we have taken alcohol, which is ethanol. If you react your ethanol with concentrated sulfuric acid at 443 Kelvin, it gives us water and alkene. Now, we will do exercise questions of NCERT, which is 9.3. Question says that For the following compound, write structural formulas and IUPAC name for all possible isomers having the number of double bond or triple bond as indicated. First is C4H8, 1 double bond, C5H8, 1 triple bond. What you have to do? Very simple. Basically, you have to give the number of possible isomers. Then second thing you should remember is the direction. If you are taking C4H8, your structure must have 1 double bond. So that is for sure. And if you are taking C5H8, the second compound, the second molecular formula, then it must have 1 triple bond. Starting with C4H8 with 1 double bond. Now the structural isomers for C4H8 with 1 double bond is given as. So first of all, it can have chain isomers. So in this, 2 chain isomers are possible. Linear butene, carbon chain with no branching. The second one is if you take a linear propene with 1 methyl group acting as an alkyl branch. So these are the 2 possible chain isomers. Because they have a variation in their chain length, they can be constituted under chain isomer. Now, next, can be derived some position isomers from these given chain isomers. So, in that perspective, 2 position isomers are possible. One with double bond present between 1 and 2 position of linear butene. So, we are talking about linear butene. And the second one with the double bond position of 2 and 3 of linear butene carbon chain. So basically, if you take the case of 2 methyl 1 propene, then the position of double bond is similar on both sides. You can take on either side, it will result in the same structural isomer. But if you are considering the position isomer for but1ene, then 2 isomers are possible in that case. So now we have talked about the 2 kind of isomers. The structural isomers includes your chain and position. Now we will move on to stereoisomers that are possible for the C4H8 formula. To do this, we will take the molecule that we already got and try to change its spatial arrangement. Now in that process, we see that only one possible structural isomer can show the cis-trans isomer, right? Now what are those? The first is cis-but2ene. So basically, your but2ene is capable of showing cis and trans configuration. So the cis-2-but2ene can contain 2 methyl groups on the same side of the carbon-carbon double bond, and trans-but2ene contains 2 methyl groups on opposite side of carbon-carbon double bond. So these are the next 2 possible isomers, or I would say specifically geometrical isomers for but2ene. Got it? Now moving on to the next compound. Continuing the solution, we can now move on to C5H8, where 1 triple bond is mandatory as per the direction of the question. Now starting with the structural isomer for C5H8, what are the chain isomers that are possible? So 2 chain isomers are possible, pent1ine and 3-methyl but1ine. So these are the 2 possible chain isomers of the molecular formula C5H8. Then after, here also position isomerism is possible. Like for the pent1ine, 2 positions are possible. It can be present on the first position and the triple bond can be present on the second position. Is it clear to all of you? Okay. Now moving on further, the next question, which is NCERT exercise question 9.6. One question is here for you from the previous part. Can those molecule with triple bond can show geometrical isomerism? No, never. Your geometrical isomerism is only exhibited by your double bond. Next question is NCERT exercise question 9.6, which asks us to show that which of the following will not show geometrical isomerism out of the given 4 options. Let me clarify the answer for you. It is option number D. Let's see how we can solve it. Before that, what are the conditions for an alkene to show the geometrical isomerism? Remember, we have talked about the condition. The first condition is that each carbon atom of the double bond must be bonded to 2 different groups. So that is for sure. Okay. Now, if that is the criteria, then the D option has 2 methyl groups bonded to the same carbon of the double bond. Okay. So what we can say about compound D, that 2 identical functional group, I would say 2 identical methyl groups are attached to the single carbon. Therefore, geometrical isomerism is consequently not possible for this molecule because you can exchange their position and that would result in the same molecule. Therefore, option D is your correct answer. Got it? Now moving on further, can we look for other molecules given in the question? Yes, let us consider the incorrect options now. Starting with option number A. So this is your molecule. So in compound A, the double bond is between two carbons, each of which has two different groups attached. This allows for possible cis-trans isomerism where the groups can be on same side or opposite side. You can look it very clearly that both the carbons have two different groups. Hence, option A is not correct. Moving on further, what is the next option? B. Here also, the groups attached to the left carbon is different, which is fluorine and chlorine. And similarly, the groups attached to the right carbon is again different, which is fluorine and chlorine. Therefore, they can show geometrical isomerism. So you have to worry about an individual carbon. Got it? The last option, which is option number C, which is to be considered. Now, if you look at this one, here in the compound C, double bond is between two carbons. Each of this have two different groups attached to it. The left carbon has C2H5 and CH3. The right carbon also has two different groups, C2H5 and CH3. Now, this configuration allows for possibility of cis-trans isomerism. Therefore, option C is also incorrect. This was all for today's class. Thank you for joining the session. I hope you enjoyed it.